the first video for our Chapter 5 notes. Chapter 5 is on discrete probability distributions. The word discrete means countable. We saw that earlier. So this means we have a countable number of values. 5.1 is on our probability distribution. A random variable is a variable typically represented by x that has a single numerical value determined by chance for each outcome of a procedure. The example right below this says, suppose you flip a fair coin twice. The outcomes are heads, 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 tails, or tails, tails. If the random variable x represents the number of heads in the two flips of a coin, find the possible values of x. The first thing to note is that the first situation that we have is heads, heads. This means that there's two different values of heads. The next one is either the first flip is a heads or the second flip is a heads. This one just has one. And the last one is both tails, so 0. So the possible values for x are going to be 0, 1, and 2. Listing those numbers in order and with commas in between them. Uppercase X is used to identify the random variable, while lowercase x is used to list the possible values for the random variable, such as 0, 1, and 2 for this example. The next thing we have is discrete and continuous random variables. So a discrete random variable has either a finite or countable number of values. The values of a discrete random variable can be plotted in a number line with spaces between each of those points, since it's not continuous. Whereas continuous random variable has an infinite many values. The values of a continuous random variable can be plotted on a line with an uninterrupted fashion, which means that they can be connected. Usually a continuous random variable is going to be something that is measurable. So we have an example right below. This says determine whether the random variable is discrete or continuous. So the weight of a steak, since we are dealing with weight, this would be continuous. It's measurable. The second one we have is the number of light bulbs that burn out in a room. There's 20 bulbs total. So for this, you can actually count those. And since it's finite or countable, we know that this is discrete. Number 3 says the amount of rain in Seattle in April. Again, amount of rain is something that you can measure, so this is also continuous. Time required to download a file on the internet, and we're dealing with time here, and this is also continuous, since it is also measurable. Right below this, it says probability distribution of a discrete random variable x provides the possible values of the random variable and also the corresponding probabilities. The probability distribution can be in the form of a table, graph, or a mathematical formula. So we have a probability distribution requirements that we have to be met. First thing is that there is a numerical, not categorical, random variable x and numerical values that are associated with each corresponding probability. The second thing is going to be the sum of all those probabilities is equal to 1. Again, this sigma, this Greek letter here, means add. So we're going to add up all those probabilities and it equals 1, where x assumes that all the possible values. The third thing is that the probability is going to be between 0 and 1 for every single value of that random variable, and it could also equal 0 or equal 1. So right below this it says determine whether the distribution is discrete probability distribution, and if not, state why. So part A, you'll notice that x is a random variable that is numerical. So that's the first requirement up here, is that x is a numerical random variable, and I'm going to put RV for random variable. The second thing is going to be we need to add up all of these probabilities. So if you take a second and add those all up, you'll see that the sum of all those probabilities equals 0.95. And if you look up above, it's supposed to equal 1, which this does not equal. And so right now we can stop and we could say, therefore, this is not a discrete probability distribution. So again, all three of those requirements must be met. As soon as one of them is not met, we know right away it's not a probability distribution. Okay, so for part B, again, x is a numerical random variable. So x is a numerical random variable. So from here, adding these up, we can see that the sum of the probabilities is equal to 1, which is what we needed it to be. And the third thing is that if you look at all those probabilities that we have, they are all either greater than or equal to 0 or less than or equal to 1. So since all three of these requirements are met, we can say this is a discrete probability distribution. Again, making sure you check all three of those requirements. Right below this is a probability histogram. And a probability histogram is the horizontal axis is equal to the value of the random variable, and the vertical axis represents the probability of each of the possible random variable values. And so remember that for histograms, you do have bars touching. So the bars do need to touch on a histogram. The example at the top of the next page says hiring managers were asked to identify the biggest mistakes that job applicants make during an interview. Does the table below represent a probability distribution? And if so, create a probability histogram. So the first thing is we have to check all of those three requirements to see that this is actually a probability distribution. So the first thing that we have is x. And if you look at x, you will notice that it is not a numerical random variable. These are categories. So no, this is not a discrete probability distribution. And the reason why is because x is not a numerical random variable. So again, as soon as one of those requirements is not met, we know that it is not a discrete probability distribution. So right below this, it says with a probability distribution, we have the description of a population instead of a sample. So the values of the mean, standard deviation, and variance are parameters and not statistics. So right below, you'll notice that there's three different formulas, and I want you not to stress about the formulas. This is more or less just showing you how these things are calculated. And again, this is for the mean, the variance, and the standard deviation for a discrete random variable. So right below, it does say, in our course, we will be using a graphing calculator to compute the mean, standard deviation, and variance. These formulas above are only given to show how these values are actually calculated. Again, we use our calculator, so these formulas are not something that you would have to use in our course. Right below this, though, is a formula that we do need to know, and this is expected value. I'll give the formula also a star. Expected value, or E of x, is the mean value in the long run for many repeated samples of the probability weighted average of all possible values. So E of x is also equal to the mean, so you can technically get this from your calculator, and it's the sum of x times P of x. And so right below this, we do have an example that says the lab orders a shipment of 100 test tubes a week, 52 weeks a year, from a supplier for an experiment that the lab conducts. Prices for each weekly shipment of test tubes follow the distribution below. And you'll notice that there's a price, $10, $12.50, and $15, and then a corresponding probability that goes with them. So it says how much should the lab expect? And as soon as you see that word expect, you know we're talking about expected value. So how much should the lab expect to budget for next year's test tube orders, assuming that the distribution does not change? And so this is a discrete probability distribution. Since x is a random variable that is numerical, those probabilities, if you add them up, will equal 1. And all those probability values are greater than 0 or less than or equal to 1. And so in order to calculate our expected value, which is E of x, this is going to be the sum of x times P of x for all the situations that we have. So the first one is going to be $10 times the corresponding probability, which is 0.4, plus $12.50 times the corresponding probability, which is 0.35, plus $15 times the corresponding probability, which is 0.25. And so from this, we're going to get, plugging this in on our calculator, we get $12.13. And this is per week, since this is how this is written up above. And it does ask for the budget for next year. And so in a year, there's going to be 52 weeks in a year. So since we know it's $12.13 per week for the year, we can do the $12.13 times 52 weeks. And when we put this in on our calculator, we get $630.76 per year that you need a budget for test tubes. The example on the next page says the Mega Millions in California Lottery and the probability of winning the Mega Millions jackpot is 1 out of 259 million. If you buy one ticket which costs $5, find the expected value of winning the $344 million jackpot prize, assuming that only one winner wins. So again, this time it does say expected value. So what's different about this problem whereas the one before gave us a table which had those values all organized already for us. So since we don't have that, I'm going to have to create a table on my own. So again, it's going to have x and p of x, a random variable, and there's two different things that are going to happen here. So either you are going to win or you're not going to win. So those are the only two things that we have. So first thing is going to be if we win and if we do not win. So let's look at the x value, our random variable, and then we'll talk about the corresponding probabilities. So what happens if you don't win this lottery? It's not that you have 0, it's going to be that you actually lost $5. So this is going to be minus $5. And what happens if you win? You win this jackpot, which is 344 million. And the only thing that we need to consider also in here is that you did have to pay $5 to play this game. I know it's not big in the scope of you winning $344 million, but we do have to take that into consideration. So I'm going to put a minus 5 in there and subtract that in just a moment. So now we have to talk about the corresponding probabilities. And it tells us that to win the jackpot, it's 1 out of 259 million. So 1 out of 259 million. And again, million has 6 zeros. So then what's the probability of not winning? So not winning, so if you subtract 1 from the 259 million, you get 258,999,999 out of that same denominator, which is 259 million. So from here, we need to calculate our expected value, which is the sum of x times p of x. And so for this, we're going to multiply x times p of x for winning. And when we do this, we have the 343,999,995 when you subtract the 5 from it on your calculator, times that corresponding probability, which is 1 out of 259 million, plus, and then we have to do this again, but for the chance of not winning. So doing this, the random variable that we have for not winning would actually be a negative 5. And then times that corresponding probability, which is going to be the 258,999,999 out of the 259 million. And so plugging this in on our calculator and rounding 2 decimal places, we get negative 3.67. So this is your expected value. What does this mean? This means that if you were expected to play this lottery many, many times, you would expect to be losing every time you play $3.67. So right now it doesn't look like the best idea to be playing this lottery. Usually if the jackpot goes up, and we have seen jackpots into the billions in California, then that's actually where you'll hear them talk about the expected value being possibly positive or closer to 0. So the example right below says, in a statistical study, individuals were asked to disclose the number of televisions that they had in their household. In the following probability distribution, the random variable x represents the number of TVs in the household. So part A says verify that this is a discrete probability distribution, which again, you have three things to check. First one is that x, which is our first column, is a numerical random variable. The second thing is going to be that the sum of all the probabilities, and that would be adding up our second column here. When you do this, you actually get 1, which is what we want. And then the third thing is going to be that all those probabilities are greater than or equal to 0 or less than or equal to 1, which they are. So yes, this is a discrete probability distribution. Part B says to draw a probability histogram. Remember, with the histograms, our bars are going to touch. So on the horizontal axes, we have our random variables, which start at 0 and go down to 9. So try to equally space these the best you can. And then once you have this all written out, you do need to make sure you label your axes. And so this is talking about the number of TVs. The vertical axis is going to represent our probability. And so if you look at the probability, the second column in our distribution, you'll notice that the largest value that we have is 0.261. And so I'm going to count by 0.1. And I'll put little middle dashes in there to symbolize that 0.05 increment. And so from here, remember, histogram bars are going to touch. So at 0, there are no probability that corresponds to 0 TVs, but at 1 we have 0.161. At 2 we have 0.261. At 3 we have 0.176. And then it jumps up to 0.186, so just a little difference there. And then we have at 5.116. At 6 we have 0.05. At 7 we have 0.25. And at 8 and 9 it's really small. It's 0.010. So this is our probability histogram. Again, double check to make sure your axes are labeled. The next thing says to determine and interpret the mean of the random variable x. So first thing that we're going to have to use is our graphing calculator. And you're going to have to take a moment to enter in L1, all of the values that we have for our random variable, which are 0 through 9, and the corresponding probabilities into L2. On your graphing calculator, you need to go to Stat, Edit, and then enter in your random variable into L1 and the corresponding probabilities into L2. Again, double check to make sure your numbers are entered correctly. Then go to Stat again, and from here you go to Calc, 1-bar stats, but since we put our information into L1 and L2, I need to tell the graphing calculator that it needs to look at L1 and L2. So we're going to go to second 1, second 2, and that way it writes both L1 and L2. And then I'm going to select enter, and from here I get my mean x bar, and I also get my standard deviation sigma x. So both of those we need for this problem. So from the calculator we get mu of x equals 3.21. I'm going to add a 0 in here. And you want to make sure that you did go to 1-bar stats. It's a great idea to write down the steps that you use on your calculator, and also make sure you tell the calculator to look at L1 and L2. So this also does say that we need to interpret. Interpret just means to talk about. So what this would be is if we surveyed, so if we survey more households, we would expect the mean number of TVs per house to be 3.210 TVs. The next part, part D, you also got from your calculator. This time it's asking for the standard deviation. And the standard deviation from your calculator is sigma sub x is equal to 1.737. Part E says, what is the probability that a randomly selected household has 3 TVs? So we are looking for probability of having 3 TVs. And you actually do have this up here, 3 TVs. If you look at this value, is going to be equal to, so the probability that x is equal to 3 is going to be 0.176, and we can get that from our table or our distribution. Part F says, what is the probability that a household has 3 or 4 TVs? So the probability that x is equal to 3 or x is equal to 4, you would find this by adding each of these up. So probably when x is equal to 3 plus the probability when x is equal to 4. And so looking at your table up here, the probability when x is equal to 3 is 0.176 plus, and then looking at when the probability is equal to 4, we get 0.186. And then adding these two values together, we do get a total of 0.362, which is our answer to part F. The last part here is G, and this one says, what is the probability that a random selected household has no TVs? So this would be the probability that x is equal to 0. And so if you look at your table up above, the probability that x is equal to 0 is that first row, and we just have an answer of 0. And there's a second question here. It says, would you consider this to be an impossible event? And no, this is just based upon this study that we had. So we'll say no. A different study, especially if you had conducted this maybe in more of an Amish area in New York. So no, a different sample would have different results. So not necessarily impossible. So at the top of the next page, it says, according to the range rule of thumb, the vast majority of values should be within 2 standard deviations of the mean. And we can consider a value that is significant is if it's at least 2 standard deviations, either away from the mean by being positive or smaller than the mean. So from chapter 3, we have the range rule of thumb to identify significant values. And so this is written down here also, along with our double arrow diagram here that we saw before in previous chapters. And so in the middle, you guys do have your mean. And being 2 standard deviations away, we have mu plus 2 sigma. So anything larger than that is going to be significantly high. And likewise, going the opposite direction of mu minus 2 sigma. And anything smaller than that is considered significantly low. It is also written in words right below the diagram. The example right below says, in the previous example, on number of televisions in a household, determine if 2 TVs is significantly low or significantly high number of TVs. So again, for significantly low and significantly high, for significantly low, we know we have to do mu minus 2 sigma, and significantly high, we have to do mu plus 2 sigma. So from part C, we know that the mean is 3.210, and we're going to do minus 2 times sigma, and sigma is given to us in part D, which is 1.737. And when we work this out, we get negative 0.264. And so significantly low is going to be a value that would be less than this or less. And then for significantly high, it's going to be the mean plus 2 times our standard deviation. And working this out on our calculator, we get 6.684. And this is or more would be significantly high. And so the question is asking, determine if 2 TVs is significantly low or significantly high. And so 2 TVs is not significant, and this is because it is between the significantly low value, which is negative 0.264, and the significantly high value, which was 6.684. So this is one way to look at significant values, is dealing with the mean and the standard deviation. And again, going 2 standard deviations away from the mean or more, which would be significantly low and significantly high. Another way to do this is to look at the probabilities, which we could have done also since we had those. And so significantly high number of successes is going to be X successes, and in trials is significantly high number of successes if that probability is really small. So significantly low is going to be where the number of successes is the probability of X or fewer is less than or equal to 0.05. So the example right below says, the following data represents the number of speeding tickets individuals received in the past 12 months. Round 4 decimal places. So you'll see 0, 1, 2, 3 are random variable, and this time it doesn't give me the probabilities, it gives me frequencies, which means the number of people that we had that had 0 speeding tickets, 1 speeding ticket, 2 and 3 speeding tickets. So part A says to construct a discrete probability distribution, and that distribution just means we need to make a table. And so I'm going to make my last column be my probabilities. I'm going to label it P of X. So in order to figure out the corresponding probabilities, we do need to add up our frequencies here. And the total for our frequencies is going to be 198. And so to get each of those corresponding probabilities, I need to take the frequency that we have, so 169, and divide it by 198. It does say to round 4 decimal places. So doing 169 divided by 198 on my calculator, I get 0.8535. And then next, taking 21 and dividing by the 198, I get 0.1061. And then taking 4 and dividing by the 198, and I get 0.0202. And it would be the same thing since it's 4 divided by the 198 for the 3 speeding ticket group. And so I have created part A, which is our discrete probability distribution. Part B says draw a probability histogram of the data. So again, remember histograms, bars are going to touch. So for this, our random variable is 0, 1, 2, and 3. And these are representing the number of speeding tickets. So make sure to label your axes. And then we also need to put in the vertical axes our probabilities. And you'll notice that probabilities are pretty small for 2 and 3 speeding tickets, but for 0 speeding tickets, it's pretty large. And so I'm going to count by 0.1. And so I have to go all the way up to 0.9. So 0.6, 0.7, 0.8, and 0.9. So 0 speeding tickets is going to be 0.8535, and then it drops drastically with 1 speeding ticket to 0.1061, and then it's very small for 2 and 3. So drawing those on there, this is my probability histogram. Again, make sure your axes are labeled. And then the next part is asking for us to compute and interpret, again, which means talk about the mean of the random variable x. And if you look on the next page, it is also asking for the standard deviation. So in order to do this, we're going to have to put in our random variable into L1. And don't forget, you need to do the probabilities into L2. On your graphing calculator, you need to go to Stat, Edit, and enter in your values for your random variable into L1 and the corresponding probabilities that we just calculated into L2. Again, double check that your numbers are all entered in correctly. Then go to Stat, Calc, one var stats, and again, since we put numbers in both L1 and L2, we need to tell the calculator to do that and look at those two columns. So we're going to go second 1, comma, which is right above a 7, second 2, close our parentheses, and then we're going to go ahead and hit enter. And from here we get x bar, which is our mean, and sigma, which is our standard deviation. From the calculator, we get the mean of our random variable x is equal to 0.2071. And again, in order to get this, we did one var stats. And don't forget to write down L1, comma L2, which is telling the calculator to look at both of those columns. It does ask for us to interpret. And so to interpret this, it would be if we survey more drivers, the mean number of speeding tickets in the past 12 months would be 0.2071. And then also from our graphing calculator, we did get our standard deviation, which is 0.5708. Part E says to use the range rule of thumb to determine whether 2 speeding tickets in the past 12 months is a significantly high number of speeding tickets. So again, for significantly high, this is going to be the mean plus 2 standard deviations. And in part C and D, we do have the mean and the standard deviation. So the mean is 0.2071 plus 2 times our standard deviation. And then substituting this in on our calculator, we get 1.3487. And so for significantly high is going to be 1.3487 or more speeding tickets. And so for this, it's asking if 2 speeding tickets is significantly high. So on this, it is going to be yes, and this is because 2 speeding tickets is more than that cutoff that we just calculated, which is 1.3487. So likewise, we're going to do the same thing for part F, but this one says use the range rule of thumb to determine whether 0 speeding tickets in the past 12 months is significantly low. Significantly low is going to be mu minus 2 sigma. And so substituting in those values that we calculated up above and plugging this in on our calculator, we get negative 0.9345. So again, for significantly low is going to be negative 0.9345 or less speeding tickets. It's a weird idea that we have a negative number here, but this just means that, just think of it as numbers and not being a realistic idea, is that what we're asking about is 0, and 0 is not smaller than a negative number, it's actually larger than. So 0 is not significantly low because it's larger than that cutoff, which is negative 0.9315. The next section is 5.2 binomial probability distributions. Experiments in which only 2 outcomes are possible are referred to as binomial experiments, provided that certain criteria is met. An experiment is said to be a binomial experiment if the 4 criteria listed are all met. The first one, number 1, says the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. 2 says the trials are independent. This means that one outcome of a trial will not affect the outcome of any other trial. Number 3 says for each trial, there has 2 disjoint mutually exclusive outcomes, which we call success and failure. Number 4 says the probability of success is the same for each trial of the experiment. Let the random variable x be the number of successes in n independent trials of a binomial experiment, then x is called a binomial random variable. Some notation that we're going to be using is going to say that there are n independent trials of an experiment. P is the probability of success for each trial, and Q is equal to 1 minus P, and that's the probability of failure for each trial. Let x denote the number of successes in n independent trials. So this means that x is going to be taking on all the values between 0 and n. And right below this we have an example that says determine which of the following probability experiments represents a binomial experiment. If the probability experiment does not represent a binomial experiment, state why. Part A says an experimental drug is administered to 100 randomly selected individuals and the number of individuals that responded favorably is recorded. Probability of responding favorably is 0.88. And so in order for this to be a binomial probability distribution, it has to meet those 4 requirements that are listed up above. So the first one is that we have to have a fixed number of trials, and we do. We have 100 trials. The next thing says that the trials are independent, and since we are dealing with people, these are independent trials. The only time that people are not independent is going to be if there's some type of relationship there. So for example, saying that maybe you have siblings or spouses or twins, so that would be something where there is a dependent. Number 3 on the list says that we have to have 2 disjoint or mutually exclusive outcomes, and we do. They're either responding favorably or not favorably to our experimental drug. And then the last thing is that we have to have a fixed probability. And our fixed probability for this is given to us. It is equal to 0.88. And so we can say this is binomial. This is a binomial distribution. Part B says a random sample of 15 college seniors is obtained, and the individuals selected are asked to state their ages. So for this, we do have a fixed number of trials, which is 15. And the trials are independent since we are dealing with people that have no relationship with one another. However, if you're asking about their ages, we will have more than 2 outcomes. So students could have been held back a year, maybe they're 19 and they're a senior, or maybe they were pushed ahead and they skipped a year and maybe they're only 16, or 17 and they're a senior. And so for this, we have more than 2 outcomes, and once we have something that one of those requirements is not met, we know that this is not binomial. The example right below says when an adult is randomly selected with replacement, there is a 0.76 probability that the person knows what Snapchat is based upon, and they give us the research that was done there. So suppose that we are wanting to find the probability that exactly 3 of the 5 randomly selected adults know what Snapchat is. Part A says, does the procedure result in a binomial distribution? So again, remember there are 4 things that we need to check that were listed on the previous page. The first one is that we have a fixed number of trials, and we do. We have 5 trials. The second thing that says that the trials have to be independent, and they are, and the reason why again is because we're dealing with people that do not have any kind of relationship with one another. The third is that we have 2 mutually exclusive or disjoint outcomes, and we do. They are going to be know what Snapchat is or don't know what Snapchat is. The last thing is that we have a fixed probability, and that is given to us in the problem, and that is equal to 0.76. Part B says, if the procedure does result in a binomial distribution, identify the values of n, x, p, and q. And yes, this is binomial because all of those 4 requirements are met. So we need to put down what the values are for n, x, p, and q. So n is our number of trials, which we have 5. X is the number of successes that we want, which is 3. Up above it says exactly 3 out of the 5 know what snapshot is. The probability of success is P, and that is given to us as 0.76. And then Q is going to be 1 minus P, which is 1 minus 0.76, which equals 0.24. As we go through these problems, they're going to be it's mostly words, and so reading and looking for key words and phrases. And so we are going to be dealing with probabilities, and many times we get these kind of key phrases. Some of us are a little bit more comfortable with these words than others, so if you feel like this is a struggle, definitely keep a running kind of list and add to it as you see different words throughout problems. So for example, the first one says at least, or another way to say this is no less than, or greater than, or equal to. And the symbol mathematically that we're going to be using is that greater than or equal to symbol. And so these are definitely something that you want to look over, make sure that you know. And again, lots of different ways that things could be worded, so maybe making a list of these and adding to them as we go through the semester. Right below that, it says when sampling without replacements and the sample size is no more than 5% of the sample size of the population, treat the selections as being independent even though they are actually dependent. Below this, we have the binomial probability distribution function. The probability of obtaining X successes from n independent trials of a binomial experiment is given by, and we have a formula there, where X is going to be from 0 all the way to n, and P is the probability of success. However, make sure to look at the stars that you have right below this, and it says, in this course, we will be using a graphing calculator to actually compute the binomial probability instead of that above formula, and that is given down below. So give that box a couple stars. So this says obtaining a binomial probability using a TI 83 or 84 graphing calculator. And so you'll notice that for this we have the first one, which is the probability that we have X is equal to X, and the second one is going to be that symbol of less than or equal to. And for these, you're going to go to second vars on your calculator, which is buttons, and that pulls up distributions. For the first one, if you have an equal sign, you use binom PDF. And if you have a less than or equal to symbol, we use binom CDF. So we have an issue here because we don't have anything with greater than. And so we're going to add in the probability if X is greater than some value. And we're going to use the complement here. So it's going to be 1 minus the probability that X is less than or equal to that value. So depending on your calculator, you might have it set up where you enter them all in almost like as in a list, as the way that it's typed in the bigger box. So it just kind of depends on your calculator or your app, so make sure you have a good understanding of how it works. But again, trials is going to be N, P is going to be that probability of success, and then it also asks for that X value, and then paste is what you would select.